Okay, hello everyone. Welcome to the Marshall W. Allworth Planetarium. My name is Jessica. I am the director and will also be your show guide this evening. You've also met Brayden and Rachel, who are two of our students. But our show tonight is exactly what it says up there, Mythbusters Astronomy. It's a really fun show. During the show, if you need to leave at any time, you're welcome to do so. You'll just exit through the same door you came in. Just, of course, be careful because it can get a little dark in here. After the show, weather looks like it's going to be good for us to do some telescope viewing. So we'll bring our telescopes out and look at the moon for sure, and we'll see what else is up out there as well. And then during the show, if you have any questions, feel free to ask. I can't always see like hands at the back where I control things, so if you're comfortable just asking your question out loud, you can do that. If you're not, then you can always ask me questions after the show as well. All right. Well, with that, I'm gonna head to the back and we'll get started. All right. So in Mythbusters Astronomy, you may not have realized it, but you have signed yourself up for a fun astronomy-themed trivia show. So during the show, we'll be taking a look at some comments, some topics. You will get to vote whether you think they are true or false. Then we will talk about what the answer is. A lot of these topics are things that are commonly misunderstood, common phrases used in astronomy, and things like that. So hopefully you're all in to participate and have a fun time. But let's get started with our very first one of the night. So our first topic, there is a permanent dark side of the moon. True or false? Do we have anyone brave enough to? Okay, I hear some whisperings. All right, at least think to yourself, what do you think it is? And let's find out if you're right or not. This is false. There is no permanent dark side of the moon. Now, I personally blame Pink Floyd for this misconception. And let's kind of look at what's going on here. So here we have our beautiful moon. This is what we see from here on Earth. This would represent like a full moon, and we see the kind of differences in the gray colors, the kind of darker gray patches. We call them Maria. And then if we head on over to the other side of the moon, the side that is not facing us, we do see, in fact, that it is dark. It is not in daylight, but that's just one point in time. So let's fast forward through time and let's see if it does stay always dark. Well, as we watch over the course of the month, as the moon orbits the Earth, we do see that this quote unquote dark side does get sunlight at some point. So, as we said, it is not permanently dark. Instead, this idea of the dark side of the moon, I think actually came about not with dark being literal, but with dark meaning unknown. Because for us here on the Earth, we only ever see one side of the moon. The same side always faces the Earth. And so until we had left Earth, the other side, we didn't know what it looked like. It was unknown to us. And so we can show this. Here we have greatly exaggerated the sizes of the Earth and the moon so that we can easily see what's going on. But as we watch the moon orbit the Earth, you can see that the same side always faces towards the Earth. Now, some people then question, well, does that mean that the moon isn't rotating? And actually, this proves just the opposite. Because, like we'll see in this animation here, if the moon wasn't rotating, as it orbited around the Earth, we would see the whole thing. We would see all sides. What's actually happening is the moon is what we call tidally locked. That means in the time it takes for the moon to complete one orbit around the Earth, it completes one rotation. So it spins in the same amount of time it takes to orbit or go around the Earth. And that's what keeps the same side constantly facing us. And so we always have the same side of the moon showing towards us. And therefore, the other side, the opposite side, was unknown or mysterious until we sent spacecraft out and were able to take images of the far side of the moon. But just to reinforce, I'm going to turn all of the shadowing and stuff back on, and we can indeed watch over the course of the month the entirety of the moon does get sunlight at some point. So on the moon, a day would actually last about a lunar year or a lunar month. Sorry, a lunar year, the time it takes for the moon to go around the Earth, which is about 27 days. So you have about 2 weeks of daytime and 2 weeks of nighttime. And that would be a day on the moon. All right. Well, let's head now to our next topic. Next up, we're going to talk about being weightless. So, true or false? Astronauts in the International Space Station, the ISS, are weightless because there's no gravity in space. What do we think? True? Okay. Let's find out. It is in fact false. So this is a really common misconception because we do see the astronauts appear to float while they're in the ISS, but that's not because there's no gravity. Now, instead of me explaining this one, I am going to let Veritasium explain this one.
Have you wondered what it would be like to be an astronaut floating around in the space station? But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating? No gravity. No gravity. Zero gravity. There's no gravity. The stuff that holds us to the planet when we spin doesn't happen up there. Gravity holds you down, so in space there's nothing there, so you just float. There's no gravity in space. No gravity, there's very little. But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture? Can you make a roughly to scale model of the Earth and the moon? And then we're going to position the space station in there. So about like that? Yeah. Now, please. Closer. About there. You ready to see the real distance? Mm-hmm. What do you reckon? Oh, it's actually about here. Maybe a little further. Now, if the moon is here and the Earth is there, whereabouts would you put the space station? Around here. Really? About halfway? Yeah. Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there. Oh, okay. The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra. But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
It's not much they float, we've seen them.
Well, clearly there's not. They're floating around.
I know they float, and the question is why?
I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here? The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them.
If the Earth didn't put a gravitational force on them, they would fly out into space, surely. Right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they?
They would still feel weightless until you smash into something.
So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
All right. So, yeah, that weightlessness that we perceive of astronauts is not true weightlessness. They are constantly falling, and everything around them is falling as well. And what essentially goes on, especially if like you were ever up there and experiencing this feeling of weightlessness, what's happening is you're just not having anything else pushing back on you to make you aware of your weight. Because here on Earth, if we're standing on the ground is pushing back up on us. Sitting in a chair pushes up on us. And we feel that support, and that makes us aware of the weight that we have pushing down. But when everything around you is falling, there's nothing to push back on you, so you feel weightless. Yeah. All right. Let's head to another topic. True or false? We have winter when the Earth is closest to the sun. What do we think? False? Okay. This one is true. It is true. We have winter when the Earth is closest to the sun. Now that sounds crazy, but that's because our distance to the sun is not the cause of our seasons. So let's dissect this one bit at a time. Does the Earth actually change how close or far away it is from the sun? And the answer to that is yes, it does. So if we were to take a look at the Earth and its orbit around our sun here, we would see the orbit looks nearly perfectly circular. But it's not perfectly circular. Our orbit is actually slightly elliptical, and it's very exaggerated in this picture, but it is slightly elliptical. So we do spend part of the time a little bit closer to the sun, and we spend part of the year a little bit further away. But as you can see here, we are closest to the sun in January, when we here experience winter, and we are furthest from the sun in July, when we experience summer. So clearly it's our distance. Our distance is not causing our seasons, or else we would see that opposite. We would also have the entire Earth would experience the exact same season all the time, and we know that that's not the case. Northern Hemisphere and Southern Hemisphere experience opposite seasons. So what's really going on? Well, our seasons are actually caused by our tilt. As you can see here, the Earth is tilted with respect to its orbit around the sun. And we will zoom out to take a look at this in our model here. Again, I'm going to make the Earth a bit bigger just so it's easier to see here what's going on. And I will move us around so that we can see our Earth. Now here I have turned on the equator and the poles so that we can get a good sense of what's going on. And if we look at Earth in June, you will see that the northern hemisphere is actually tilted towards the sun. With its northern hemisphere being tilted towards the sun, that means the sun is higher in the sky, it's up for a longer period of time, and that sunlight, put it on the wrong side, that sunlight that we experience is coming almost, straight, not all completely straight down, but it's coming at a steep angle. And that concentrates a lot of the heat into a smaller area of the ground. So all of this leads to the northern hemisphere of the Earth getting a lot of energy, a lot of heat, and that causes the Earth to heat up. Now, 6 months later, when the Earth is on the other side, we see the northern hemisphere is tilted away. And so we end up with the exact opposite. The sun is lower in the sky, it's not up for as long, and that light is more spread out. So you don't get as much energy concentrated in the ground, it's more spread out. All of that leads to there not being as much heat, and so the Earth cools down. And so it is our tilt that creates our seasons. And of course, we can see why we have opposite, because when we're tilted away, the southern hemisphere is tilted towards. So when we have winter, they have summer, and vice versa. Say it a little bit louder. Yeah, so even in like the hemisphere, when you're closer to the equator, you're going to get more extreme heating, and closer to the pole, you're going to get less, which is why we see that temperature difference among the hemisphere. Yeah. So if we have a time tilted most towards and a time tilted most away, we also must have a midpoint, and this is what we refer to as the equinoxes. And that is when we are neither tilted towards or away. We use that as like our transition period. So our spring and fall seasons are during this time period. So speaking of equinoxes, our next topic is about something that may or may not happen during the equinox. So let's take a look at that. Here's our next question, true or false? It is much easier to balance an egg on the equinox. Has anyone heard of that, first of all? It is something that gets spread around social media around the equinoxes. Okay, so this was before the time of social media. This is an old wives' tale, but it is in fact false. So the idea behind this wives' tale, this idea that you could balance an egg more easily on the equinox, is because during the equinox, since we are neither tilted towards or away, that led some people to assume that the sun must be directly overhead, and therefore you have some extra gravity from the sun pulling up on the egg, making it easier to balance it against gravity of the Earth pulling it down. Now we can very easily test every part of this. First, let's test the idea that the sun is directly overhead on the equinox. Here we have the sun on the spring equinox for here in Duluth, and no, it does not get directly overhead. We're looking at, maybe 43 degrees, not directly overhead, because the Earth is curved. The Earth is a sphere. So if you were standing on the equator at the equinox, the sun would be directly overhead. But anywhere else on the Earth, that's not going to be the case. Now, if you want to get even more in the weeds with this, if you were to actually do the math of how much force the sun would pull upward on the egg if it was directly overhead, that ends up being very, 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 very small, negligible, not going to affect anything. So what I think happened to kind of propagate this idea is people heard it and decided to test. They say, okay, it's the equinox, let's try and balance an egg. And they were successful. But that's not a complete experiment. Because if you're going to test if it's easier to balance an egg on a specific day, you have to compare to other days as well. And if you were to do that, you would find it's just as easy, or really probably just as hard, to balance an egg on its end any day of the year. So yeah, that's that fun little wives' tale there. All right. We have a couple more topics. Let's head over to Jupiter to take a look at another one. So true or false? Adding a small amount of mass to Jupiter would turn it into a star. Okay, let's see. This one is false. Yeah. So this idea starts because if we look at what Jupiter is made of and we look at what stars are made of, they're actually very similar. Jupiter and stars are mostly made up of hydrogen and helium. However, Jupiter is much, much, much smaller than a star is. So just compared to our sun. Our sun is about 100 times the size and about 1,000 times the mass of Jupiter. So adding just a little bit would not get it anywhere near to the size of the sun. But, you may ask, are all stars the same size as our sun? And no, they're not. There are, in fact, stars that are smaller than our sun. The smallest of which we call red dwarfs. And the smallest red dwarf is actually not that much bigger in size than Jupiter. However, it is still much more massive. It's about 80 times the mass of Jupiter. So theoretically, if you had 80 Jupiters and you smush them all together, you could feasibly turn them into a star. But that's more than a little bit of mass being added to Jupiter. If you wanted to turn it into a star, you would have to add quite a bit more to make that happen. And you would have to make sure that what you're adding is mostly hydrogen and helium, because what makes a star is at the center that hydrogen is being fused into helium. And this nuclear fusion is what powers a star and makes a star a star. So, not completely impossible. It can feasibly happen with enough stuff being added, but it would take more than just a little bit of mass to turn Jupiter into a star. So maybe it was a little tricky with the wording on that one, but you got it. So, all right, we have 2 topics left. Here is our next one of my personal favorites. True or false? Stars do not move. All right, I'm hearing lots of good variation in this one. Let's find out. This is false. So, in our lifetime, if you were to sit here and watch the stars every night for the duration of your life, it's true that you would not see much movement. You really wouldn't see the stars move. But they are moving because our sun and all of the stars in our galaxy are orbiting around the center of our galaxy. And they're all moving at slightly different speeds. So while it's not something you can easily see during your lifetime with the planetarium, time is something that we can easily meddle with. So if I start progressing forward, let's say 1,000 years at a time, if you watch, you can slowly see a couple of stars starting to move, some of the constellations getting a little bit warped. But even this is not very long time scales, at least in terms of, astronomy. So let's bump this up. Let's increase it by 10,000 years at a time. And when we do that, we can really see the stars moving. And the patterns that we recognize are pretty much gone. So yeah, stars do move. They're just moving at rates that we don't really notice in our lifetime. It takes thousands and tens of thousands of years for the movement of the stars to be noticeable. All right. Ready for the last one? Okay, here we go. Black holes. True or false? Black holes suck everything in. It is false. Black holes have a really bad rep. They're kind of like the cosmic boogeyman, and I don't think it's fair. So let's talk about first what a black hole is. It's an object that has so much mass condensed into such a small volume that its gravity is the most extreme. Its gravity is so strong that you cannot go fast enough to escape from it. Not even light travels fast enough to escape from it. And that's why they're black, because light doesn't come from them. Light can't escape. But the thing is, that's not everywhere around a black hole. That's only once you reach a certain point, which we call the event horizon, the point of no return. Once you cross that, yes, you're done for. You're falling in the black hole, you're not getting back out. But as long as you stay outside of the event horizon, you're fine. And the event horizon of a black hole is actually not that big. So if you were to take, say, for example, our sun, and you instantly replaced it with a black hole of the same mass, nothing would change in our solar system. Well, I mean, we'd freeze to death, but the orbits and stuff wouldn't change. Not even Mercury would get sucked in because the event horizon of a black hole of that size is a couple of miles in size. You'd have to get a couple of miles from the black hole in order to be sucked in. As long as you're outside of that, it's just gravity. And it works the same way gravity of any other object works. Orbits would keep going, we'd be fine. Yeah. So then, to end us off, we always then get asked the question of, well, what happens if you do fall into a black hole? And I will finish off letting none other than Neil deGrasse Tyson explain to us what happens then.
And now for another installment of What If? You ever wonder what would happen if you fell into a black hole? First, some background. Black holes are regions of space where the gravity is so high that the fabric of space and time is curved back on itself, taking exit doors with it. Light is the fastest stuff in the universe. Not even light can escape. Light can't escape. Neither can you. Which is why we call these things black holes. This boundary within which light cannot escape, we call that the event horizon. All the stuff within the event horizon has collapsed to an infinitesimal point at the center. Ready? Here we go. I'm going to fall to the black hole feet first. As I get closer and closer, the force of gravity grows astronomically, but I can't feel it. Because, like anything else in free fall, I'm just weightless. But I'm starting to feel something else. Something sinister. My feet are closer to the black hole, so gravity pulls on them harder than at my head. This difference in force from head to toe is normally tiny, and it goes unnoticed on places like Earth. But in a fall towards a black hole, this stretching force, all you notice. If I were made of rubber, then I just stretch. But our bodies are made of things like bones, muscles, and organs. I would stay whole until the stretching force exceeded the molecular bonds in my body's flesh. At that moment, my body would snap into two segments. That's not even the worst part. Everything of me that ever was gets funneled to the black hole center. So not only have I been ripped in half, I'm being extruded through the fabric of space and time, like toothpaste through a tube. As I keep falling, the difference in gravity continues to grow, and each of my two body segments snaps into two more segments, and so on, splitting my body into ever-increasing number of parts, all the way down to the atoms themselves, and beyond, leaving an unrecognizable array of particles that just a few moments earlier had been me. We have a word for this cause of death. Spaghettification.
Yes, that is in fact the real word. It is my absolute favorite term in astronomy, spaghettification. And that's what happens to anything that crosses that event horizon and falls into a black hole. I think that is a super, super fun way to end the show. Hopefully, visuals weren't too gruesome. We are heading into spooky season after all. All right. So with that, I'm going to bring our lights up and see were there any questions that anyone had. Ooh, the closest black hole to us. I don't actually know for sure, but I know it's at least several thousand light years away. So really nowhere nearby. Any other questions? Yes, anything that gets too close to it, yes. But if you were just flying by, you're not going to get just sucked into the black hole. You have to pass that point of no return. Not today. I believe it's tomorrow is the equinox. I meant to look it up. The 23rd. The 23rd is the equinox. So if anyone wants to experiment on balancing an egg, you can start doing it now, leading up to the equinox, and you can try for yourself. All right, then. Well, thank you all so much for coming out. I hope you enjoyed the show. Like I said, we should have telescope viewing out in front of the planetarium. And I will be here if you have any questions. There are also star charts and fun things that you can get sitting on the table in front of the TV. Please take stuff if, to have. And yeah, thanks again so much for coming out.